I had a really quick question about like the exam. Will there be a exam review session like in class, or will that just be during office hours? I don't remember if you brought that up.
Yeah, it'll by the way, we're recording now, just so you know. Um yeah, it'll probably be during on-office hours session. We'll either schedule it separately or it'll be during office hours. There's no homework due that week, for instance, and so the office hours might be a particularly good time to do it.
Okay, thank you.
Hmm. Okay.
That's next week, right? Or
The
when is
exam
it?
is not next week, no.
Oh,
The exam is going to be sometime during like week 7. Let me just pull up my syllabus real quick if I can find it. Let me see. Okay. Can you guys see my syllabus when or am I not sharing that screen right now? Can you guys see the syllabus now?
yeah.
Okay, cool. Yeah, so right now we are here. The exam is going to be during this week, so the week of 10/26. Okay?
And
Um,
and the exam will cover everything like up to week 7, or will that also include week 7?
the exam will. I just got a package. Okay. The exam is going to cover everything that ends at homework 5, and I wanted to mention something to you guys actually. Homework 5 I will likely make due on Friday. I'm not quite sure exactly yet. Depends on how far we get over the next couple lectures. Um, but there's like a nice stopping point, basically after the lecture that's currently planned on 10/21. And so most of what I would cover on homework 5, you can do with the stuff that you've already that we will have learned this week. But there are there are a couple problems where it makes more sense to stick it on to homework 5, and so we might make it due on Friday. But I'll let you guys know about that soon. And then the exam will cover, like I will not test you on anything that you have not had practice on in the homeworks. The homework 5 will likely not be graded by then, because you'll have turned in your homework just a few days before. Um, but you'll see the solutions and stuff, and then hopefully you'll have office hours and stuff like that. Okay, and then again, week 7 will be when the actual exam is, and we'll try and schedule something soon.
Thank you.
Yep. Other questions? All right, I'm gonna go back to the OneNote. Let me yell if my mic runs out of batteries again. Okay. You guys can see my OneNote now, hopefully. Yes. Cool. All right. Here's where we were before. We were talking about this problem called Stokes' first problem. And in this particular problem, we were talking about a plate that's suddenly set in motion below an infinite amount of fluid. And then we were able to go through, or we determined that we have this partial differential equation, but then using this technique called a similarity solution, where we let this variable c be expressed as some combination of the y and t variables, we were able to turn this partial differential equation with 3 boundary conditions into an ordinary differential equation right here with 2 boundary conditions, because 3 of them collapse onto 2. And then on Friday we went through the actual solution of this ordinary differential equation, and then did some analysis on that. So where we're going to go today starts off sort of a few different lectures on this sort of general solution technique. And what we're talking about now is, instead of where we have that one fluid that extends infinitely into space above a plate that's suddenly set into motion, what if instead still the plate is set into motion, but instead of an infinite amount of fluid above that plate, now we have a finite amount of fluid with a thickness, let's say h here, okay? axes here being x and y in that direction. Okay, so the actual derivation of the governing equations and stuff look basically the same. I'll just go ahead and skip and combine some of the steps because we've seen this already fairly recently. So I'll say let f equal vx over u to make it non-dimensional. Okay. Then what we have is we can simplify the Navier-Stokes equation to look something like this. Sorry, that should be a y on the bottom. Okay. Excuse me. Again, this nu here is a kinematic viscosity. And then, of course, we have boundary conditions as well. So we have at t equals 0, that's our initial condition. Okay, then we have Vx is equal to 0, and therefore F is equal to 0. Okay, so initially the fluid is not moving. Then we have a boundary condition 1. This is at y is equal to 0 at the bottom plate. Okay, we have Vx is equal to u, and so therefore F is equal to 1. And then boundary condition 2 is that at y is equal to h now, rather than y is equal to infinity, then we have Vx is equal to 0, and so therefore F is equal to 0. Okay. Okay, so what I'll mention, and I'll write this down in just a second, or here, I'll go ahead and write it down. Basically, before, when we were talking about Stokes' first problem, okay, we had F depends on y, t, and nu, right? Okay, and if you remember what our argument was, is that because F is non-dimensional, then it makes sense for F to depend on something that's also non-dimensional, and the only way we can find some combination of these three things that are non-dimensional is that y squared over nu t thing, or what we ended up using, which was y over square root of 4 nu t, right? So we said F depends on y squared over nu t because it is non-dimensional, right? Now what we have is this additional thing. It depends on y, t, nu, but also there's an h. Okay? And so what that means is now there are other ways of combining these parameters to make things non-dimensional, right? You can imagine that, okay, so we said f is non-dimensional, so it has to depend on something that's also non-dimensional, and the only way of combining the parameters is y squared over nu t, or some function of that, right? Now there are other parameters that could be non-dimensional as well, right? So now, for instance, y over h is also non-dimensional. Right? So maybe f does not just depend on y squared over nu t. Right? Now, it was really convenient last week when we were able to say and then show mathematically later on that f depends on only this, right? That let us put in this c, and then we basically converted this PDE into an ODE, right, as we talked about at the opening of this lecture. Okay? Unfortunately now, well, now maybe it's good that f can actually depend on several different things now, basically, right? What I'll say now is that the solution can depend on y, that should be a y, for some reason it looks like a g, and t independently right? Before, we could only have f depend on the two parameters together, on xi, which is y over square root of 4 nu t, right? But now our solution can depend on y and t independently because you can find ways of expressing both of these things non-dimensionally, right? The reason is because y over h is a non-dimensional length, right? And then, of course, t over h squared over nu is a non-dimensional time. Okay? And we'll use that later on when we actually take this whole equation and make it more non-dimensional, but we don't need to worry about that quite just yet. Okay? Now, if we had not decided to go through this analysis and think about this way, we could have also just tried to charge ahead and then do our similarity solution. Right? So instead, let's just try our similarity approach. Okay. If we try our similarity solution, right? This is how it worked. We said we have a xi here that we're going to define as y over square root of 4 nu t. And then we do all the fun chain rule things, right? And then stick that into this equation here, right? Well, it turns out that this equation is actually exactly the same as the equation before. If you don't believe me, I'll page back and show you, but hopefully you can take my word for it. Okay. If you then stick this into the equation, then you get the same equation that we had before. And the solution method for that equation is basically the same as we had before as well, right? If you recall if we recall what we did is we set, like, let's say call it G defined as df dxc, and then we solved that differential equation because that becomes the first order OD, and then we integrated that. Okay. Here's where the problem comes in. If you recall, we also have to, everything we do to the PDE, we also have to remember that there are boundary conditions, and 3 boundary conditions in this case. Right? So here's our initial condition, but we
I think your mic just cut off.
we're back. Okay, I hadn't used my mic in a while. You can hear me now, right? Cool. And we're back. Okay, where were we? I think you guys got to this point, right, where we're talking about that, and then we were talking about the 3 boundary conditions, okay? So one of the boundary conditions was that f is equal to 0 at time t equals 0. That was the initial condition. And when time t equals 0, then that implies that c goes to infinity. Okay, like this. We have another boundary condition. That was that f is equal to 1 at y equals 0. Well, when y is equal to 0, then c goes to 0. Okay, so that's what we get when c is equal to 0. The problem, though, is that we have a third boundary condition here. And at this third boundary condition, when f is equal to 0 at y equals h, y equals h there. When y is equal to h, what we actually have is c is equal to h over square root of 4 nu t. Right? And so what we have is a second order differential equation here with 3 boundary conditions. And so we can't solve that. the problem is actually overspecified. You're not going to be able to find a function f that's able to that satisfies this ODE, that simultaneously satisfies all three of these boundary conditions. Okay. This is the key difference from what we had in the similarity solution, because if you recall in the similarity solution, what we said is that at boundary condition 2, y is equal to infinity, or f is equal to 0 when y goes to infinity. Well, when y goes to infinity, then c also goes to infinity. And then we ended up copying this first boundary, this initial condition right here. And we actually ended up only having 2 boundary conditions, right? That's not true in this case. In this case, we actually have 3 boundary conditions, and so it can't work out. You can see immediately that like this argument up here based on different units and non-dimensionality and stuff like that, it's because now we have this h factor in our problem statement here. And so everything can be in terms of y over h, yada, 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 right? Or what this means is that when there's an h now, you end up with having a 3rd boundary condition, and it's sort of like too much of a good thing, if you will, right? So you're over-specifying the problem. So we need a different solution method, right? Okay. All right, I'm going to introduce that solution method in just a second. Okay, but first, you know, we talked a little bit about these dimensions and units and stuff like that, and so let me go ahead and non-dimensionalize this equation just to make things a little bit easier, so we don't have to worry about all these h's and new's and stuff like that. Okay, so I'll say first, I'll just say non-dimensionalize the equation, the problem. Okay, the way we're going to do that is basically, well, before we are already done this, so let me just reiterate this. F is equal to Vx over U. We'll also let this y squiggly thing be defined as y over h. Okay, and then we'll let t squiggly be defined as t over some time scale here, tau. I already wrote up here what this time scale is going to be, but I'll show you here that it makes sense for this tau to be given by this time scale. Okay, have any of you guys done non-dimensionalization in solving equations and stuff, perhaps in other fluids classes or like a heat and mass class or something like that? Shake your head if the answer is no. Awesome, cool. Let me go through it very in a more rigorous way, and then we can talk about ways of making this basically less vigorous, basically, or just less rigorous, or even faster. The left-hand side of that equation is dvx dt, right? I had actually already eliminated one of those things up here, but the actual in the Navier-Stokes is actually dvx dt, right? The way that we can non-dimensionalize this is to basically just apply the chain rule a few different times. Okay, this is equal to df dt squiggly times dvx df times dt squiggly dt. Right? You guys can kind of see that chain rule here, because the df here cancels with the df and the dt squiggly cancels with the dt squiggly, right? And then based on these definitions, you can write down what these things are. Okay? df dt squiggly will keep in front. Okay? dvx df is actually just u, right? Because Vx is equal to U times F, and so dVx dF is equal to U. And by the same logic, dt squiggly dt non-squiggly is 1 over t. Or sorry, 1 over tau. So let me just write it a little bit more neatly. That looks like this. Okay. You know you did this right because your final term here has to have the same units as your original term here. The original term here has units of velocity over time. the final term right here has units of velocity over time times something that's non-dimensional, right? F is non-dimensional, and t squiggly is also non-dimensional. Okay. And so this is the rigorous way of doing it. I don't expect you guys to do it every time. What you can basically do in all these cases is you see something that has units of dvx dt, or has units of, velocity over time. And so you take the non-dimensional analog, and then you just make sure that it has the right units in front. You have a u on the top and a tau at the bottom. Okay. For example, the right-hand side of that equation looks like this. Okay. And so what you would expect then is 1 unit of velocity on the top and 2 units of length on the bottom, because the y has units of length on the bottom, or y is in units of length, and that length scale is h, right? And it's 2 units because you're taking a second derivative, so you take a derivative twice, right? It's like meters per second squared or something like that, right? And then, of course, your non-dimensional analog. Okay? And so the way this works is then your original equation was dvx dt equals nu times d squared vx dy squared, right? And so it's just a matter of plugging this in and then showing that everything kind of cancels. So on the left-hand side, you have that. And on the right-hand side, you have that. But here, I'll redraw this a little bit. You have the nu times this. Okay. And this is where it comes in, where we let tau equal h squared over nu. And so we can instead define our non-dimensional time as t over h squared over nu, right? If that's the case, if tau here is equal to h squared over nu, then then what we have is the PDE becomes this. If I can draw that better. Okay, because everything cancels on both sides. And then, of course, we have our 3 boundary conditions. That's f equals 0 at t equals 0. Here we have f is equal to 1 at y is equal to 0. And f is equal to 0 at y is equal to 1. Okay? Does that all kind of make sense? This is how, in general, we non-dimensionalize equations here. Please ask me questions if, for instance, this is the first time you've seen this, and none of this really makes sense to you. Okay? The reason why we do this is because in our equation now, we don't actually need to take any sort of parameters into consideration at all. Okay? So there's no h here anymore. We were able to non-dimensionalize that out. There's no nu at all anymore here either. Okay. And that's convenient because, for instance, you could imagine that if you were to do this in a less efficient way, you could try and solve this problem for one value of h and then have to solve a different problem for a different value of h, right? If like, I could give you several different homework problems and they all just have different values of h or something, you'd have to redo the problem over and over again. Instead, if we do it like this, then you just do the problem once and then you just express everything in terms of this non-dimensional solution and then rescale the length scale or the time scale or something like that to get the problem that we actually need. Okay? Okay, so that only got us to basically this point, but now we actually need a way of solving this particular problem. Let me go ahead and do that. Real quick though, I'm going to solve a different problem because this problem is actually it's not really the best problem to start off with. And so let me start with something a little bit different. Okay. I'll just say, let's do a different problem. And I'm going to connect that to the problem that we actually talked about earlier in maybe a lecture and a half away, okay? But just bear with me for a second. Okay, the problem that we're actually going to do now is this. So still same geometry. We have a fluid in between two plates. Before we had above we had in the case where basically at time t equals 0, this bottom plate is set in motion suddenly to the right. Okay, this particular problem, I'm going to have this plate moving this way. It had been moving that way for a long time, and so it develops this flow profile that we're all quite familiar with at this point. And then at time t equals 0, we have no motion at all. Okay, here now u is equal to 0. Okay, same geometry as before. So x is this way, y is this way. Here's y equals 0, and y is equal to h. Okay, so in other words, let me just sort of picture what this is. You have something that's, you have a fluid now that's moving to the left, or the bottom plate is moving to the left. It had been moving like that for a long time. And then all of a sudden at time t equals 0, the bottom plate stops. And you're seeing sort of how much, like how does the fluid actually slow down and stop? Okay, everyone still with me? I'll connect this, like I said, in a couple lectures to where we actually, to this actual problem that we started off with, okay? But instead also, instead of calling this F, I'll call this G now. Now this equation looks like this. Still the same governing equation because we're dealing with an Navier-Stokes equation. Okay. But the initial condition now is that G is equal to y minus 1 t equals 0. Okay, perhaps you guys can see that. Initially, it looks like this. And so at y equals 0, my g is going to be equal to minus 1 or minus u, right? And then it increases linearly until at y equals 1, my g is equal to 0, okay, because the no slip up here. Okay, and then of course we have two boundary conditions. And those boundary conditions now are no slip at the top and bottom. And of course, the plates are not moving. And so we have G is equal to 0 at the top and bottom. Okay. And I'm going to get sloppy real quick. I'm just letting you guys know that. I'm probably going to stop writing all the squigglies. Let's just make it implied in the future that whenever I write a y or a t, there's actually a squiggly over it. Okay. Just because we're only going to use the non-dimensional form here at all. Okay. So the way to solve this problem, this is again a partial differential equation with 3 boundary conditions. 2 in y and 1 in t. We're going to use a new solution method that's called the finite Fourier transform method. And I'm going to write this with better handwriting so that you guys can look it up if you wanted to. Okay, we call this FFT. And it's a pretty useful solution method that we're going to use that we're going to discuss over the next few lectures. If you're following along in the textbook, this is in Dean chapter 5. Okay. The fundamental way that these solutions work is we have to make a postulate here. Okay. So we will claim that we can write the solutions in this form. My g, which is a function of y and t, can be written as a sum, an infinite sum of solutions or of functions that look like this. This is a capital phi here. Okay. Where these functions, capital phi, are written like this. Okay. This is kind of a bold claim. I'll show you guys later on that this is definitely true, and you can write functions like this. But maybe I can draw a few analogies first to maybe convince you guys that this could be true. Okay. These functions here are called basis functions. They're actually called orthonormal basis functions. Okay. Phi n are orthonormal basis functions. What that implies is this property. If I were to integrate from 0 to 1, the product of two separate basis functions, phi n and phi m, like this, then that gives us this. And you guys recognize what delta mn is. That's the Kronecker delta, right? 1 if m and n are equal, and 0 if they're not equal. Okay, there's a reason we call this orthonormal basis functions. That's because when we're talking about unit vectors, for instance, another way of calling unit vectors, of thinking about unit vectors, is that the unit vectors are a basis for all the different vectors that are potentially possible. That's basically what we're talking about here. By the way, this relationship that I wrote out, if you don't believe me, you can open up Mathematica or just get really good at integrals and then actually multiplying these out and showing yourself that this is true. Okay, and I invite you to actually do that. Okay, so basically just take, let's say, square root of sine 1 pi y and multiply that by square root of sine 2 pi y and then take this integral and you'll find that it's equal to 0. Or if you take square root of sine pi y times square root of sine pi y, then you'll find that it's equal to 1. Okay, trust me, it totally works out. Okay, but that's basically what this means, is that if I were to take two of these basis functions and multiply them together, as long as n and m are the same, then you get something that's non-zero. Okay, now back to this idea about basis functions. Okay, I'll just write, does this look familiar? Okay, and that's because we've basically talked about this already. This was sort of the first thing that we talked about in lecture 1 of this class, right? If you recall, one of the key concepts that we talked about at the beginning of the class was that a vector A can be written, sorry, not to infinity because we're not in infinite dimensional space, can be written as a sum of coefficients of unit vectors, right? Now this was sort of a Freudian slip or just maybe an honest mistake where I turned this top thing into an infinity, because when we're talking about functions here, then the top actually does have to be infinity. Can you kind of see the analogy between these two things here? Right? The difference is that a vector has only 3 components. It's only in 3-dimensional space. And there's actually only 3 numbers in a vector, right? 3 numbers exactly determine a vector. 3 scalars determine a vector, right? And so that's why the sum goes from 1 to 3. Whereas a function has infinitely many values between the values of 0 and 1. If it has infinitely many values, then perhaps you can like you can follow that you need infinitely many of these functions to be added together to completely determine the sum. Okay. And basically, this is just saying that this equation is true basically for any given time, right? And so don't worry about the time component here. I could have written, g of y0 is equal to g of n is just equal to some sort of coefficient times, or scalar, if you will, times a basis function. Okay. So pictorially, what this is saying is, if I have some sort of vector here, a sub n, that's equal to the sum of some amount of E1, some amount of E2 times A1 plus A2 plus A3, etc., right? And what this is saying is that my unit vector, or my unit vectors are now called basis functions, basically. And the basis functions here look something like this. If we have just any function from 0 to 1, that, I don't know, looks something like this. That's a terrible function, my apologies. Let's just say any function that looks like that, let's say, right? That can be written as a sum of several different functions. This is what phi1 looks like. This is what phi2 looks like if I were to plot these actual basis functions, etc. And I should be able to add all these up and eventually get something that looks like this function. Okay, does that kind of make sense? Okay. Now, if that is true, I forgot my coefficients here, sorry. So here's a g1 of t, and here's a g2 of t, okay? Okay, now if that is true, then in both cases, my basis functions, or unit vectors, are orthonormal, right? Because you know that if I have two unit vectors and I dot them together, then this is just equal to delta mn, right? E1 dot E1 is equal to 1, E1 dot E2 is equal to 0, et cetera, et cetera, et cetera, right? That's essentially what I'm saying here. What I'm saying is that if I were to dot two of these basis functions together, when we're talking about functions, we no longer call it a dot product. We write it like this. This is called an inner product. Okay. It's defined exactly as we drew, or as we wrote up there, where we basically multiply the two functions together and then integrate over the domain. In this case, the boundary conditions go from 0 to 1, and so we integrate over that. This also gives us delta mn. Okay, and so you can think about this not as a dot product, but this is called an inner product, but it's basically the same thing as a dot product, right? Now the dot product is kind of cool in the vector world because the dot product allows us to calculate what the different components of my vector actually are, right? You know, for instance, that if I wanted to find a component an of a vector, then I just need to dot that vector with a corresponding unit vector, en. The reason why this works out is something that you guys are already familiar with because you're experts in index notation at this point, and vectors and tensors and stuff, right? Because you know that when I substitute in something like this, that's A, right? If I were to dot this with en, then when I dot this with en, then I still get a sum when m goes to 1, sorry, not infinity. I keep doing this Freudian slip here. It's actually 3. When m goes from 1 to 3, I get a Kronecker delta, right? And you guys know this Kronecker delta trick, right? Because in this sum from 1 to 3, only one of these terms is non-zero. That's the term where m happens to be equal to n. And so then this gives us a sub n, right? And so that is exactly why, because of this relationship with the dot product and because our unit vectors are orthonormal, then we can use this dot product to determine what the coefficients are of any arbitrary vector. Likewise, I won't write it out on the right-hand side, but it's exactly analogous, and I'll encourage you guys, after the lecture, to play with this yourself and convince yourself that this is true.
I had a question really quickly.
Let me go ahead and write this down, and then I'll get to your question. Okay. Likewise, Gn of t can be written as the dot product of our original function and one of our basis functions. Just like how on the left-hand side, if I wanted to find a component of a unit vector of my original vector, okay, then I just take my original vector and I dot it with that unit vector. Here, if I wanted to find the component, or the coefficient is what it's called over here, of this basis function from my original function, I take my original function and I dot it, or in this case, take the inner product with that basis function. And of course, this operation, an inner product, is defined as multiplying those two functions together and then taking the integral. Nikhil, what's your question?
When we're taking our spectral functions, do they all have to be vector valued, or can they be like scalar valued as well? Like, doesn't matter.
When we're taking our what?
Like the inner product of like our basis functions, do they have to be vector valued? Right.
Everything here is actually only scalar valued.
I'm sorry?
Yeah, so everything here is scalar valued. So the G, well, the left-hand side, we're talking about vectors, it's a different analogy, but everything on the right-hand side is scalar valued. Nothing here is a vector at all.
Okay, okay, thank you.
Any questions? So again, this is a bit of a leap, but hopefully I've been able to draw a little bit of an analogy and hopefully not make this too much of or not make this too uncomfortable for you guys. But the idea is that just like how a vector can be written as a sum of various unit vectors times coefficients, my function can also be written as a sum of various coefficients times unit vectors, or in this case, basis functions. Okay, why would we do this? Okay, obviously the answer is because it actually allows us to solve the problem, right? So here's why we would do this. Let's take the inner product of my partial differential equation up here with one of these basis functions. Mathematically, all that means is I'm going to multiply both sides by phi n and then take an integral. And I'll show you guys what this actually does to both sides of the equation. It does something really neat and allows us to actually solve this equation. Okay, so I'll say perform inner product on the PDE. Okay, the left-hand side looks something like this. Okay, and the right-hand side looks something like this. Okay. Now, I can simplify these things, both of these sides, considerably. Okay. The left-hand side is actually the easiest one. The left-hand side looks like this. The integral from 0 to 1 of dg dt phi n of y, well, that's just equal to that, right? I'm just exchanging the order of the integral and differentiation, right? And I'm not talking about a moving control volume or anything, so I don't have to do Reynolds transport theorem. You know, I can just switch the order of integration and differentiation. Okay, but this thing on the right over here now is basically this. Okay, and so this is basically a time derivative of all of my coefficients. Okay, the right-hand side gets a little bit hairier, but we'll get through it. Remember how last week I mentioned integration by parts? We need to actually do integration by parts here now. Okay, so the right-hand side looks something like this. Okay, if I do integration by parts once, this is what I get. Okay, I know that some of you guys might be kind of rusty with integration by parts. That's totally okay, but maybe the functional form of this looks familiar enough that you can believe what I'm saying. Nod your head if you agree. Okay, cool. All right, we can actually do it one more time. So we have the same thing over here. And now we just need to do integration by parts on this guy one more time. Okay. Now there's a reason why we would do all of this. It's because once we do the integration by parts, we can simplify this equation on the right-hand side significantly, or this expression on the right-hand side significantly. Okay. For instance, let's look at this first term right here. Let me write that down again. dg dy phi n at y equals 0 and y equals 1. Okay. This expression is actually equal to 0. Okay. Here's why. If we go back up here and we look at our basis functions right here, square root of sine n pi y. Okay, and we're trying to evaluate this at y equals 0 or y equals 1. Let's see what happens at y equals 0. When y equals 0, then the square root of then the sine of n times pi times 0, so the sine of 0 is always going to be 0, right? When y equals 1, then the sine of n times pi, where n is some integer, is also equal to 0, right? Because, you know, if you go around your circle like this, right? Sine of 0 is 0. Sine of pi, or 1 times pi, is also equal to 0 because you're over on this side of the circle. Sine of 2 pi is equal to 0, and et cetera, right? And so this expression right here is actually equal to 0 because phi n is equal to 0 at y equals 0 and y equals 1. Okay. Now it turns out that this other equation here, or this other expression, this other term, is also equal to 0 for a slightly different reason. Can anyone guess why this is equal to 0?
From the boundary conditions.
From the boundary conditions. Okay. If you haven't seen it really quickly, you know that g is equal to 0 at y equals 0, and g is also equal to 0 at y equals 1 because of this. Right? We define our boundary conditions such that g is equal to 0 at both y equals 0 and y equals 1. And so therefore, this second term here is also equal to 0. Was there a question?
Yes, sorry, could you not apply that same like line of reasoning for the first term also, right? Because we're saying that g yt is equal to the product of g n of t and phi n of y, right?
You mean right here?
Right.
Yeah, but that's the derivative. The derivative of g is not necessarily equal to 0.
I'm referring to phi though, because we're saying that we know that g is a product of phi and like g sub n, right? So like even if we didn't know the form of phi, like we could still say that phi n of 0 should equal 0 because of the boundary condition as well, right?
Yes, but why do we need to actually do that? Because we already know that phi n is equal to 0, and so that's like saying, you know, if you add up all the phi n's and it gives you 0, then then the individual ones already give you 0. Then there's no reason to have to add them up originally, right? This also gets into something maybe a little bit more subtle when it comes to Fourier series and stuff like that, but we can get into that separately, maybe during office hours or something. Okay. So this is kind of cool. At least I thought it was kind of cool. Because once we do this integration by parts, for various reasons, all of these things actually reduce down to 0. Okay. This first one reduced down to 0 because we were magical in how we chose our basis functions. Right? We happen to choose basis functions, this square root of sine n pi y, such that we get 0 when y is equal to 0 and y is equal to 1. Right? And this one is actually equal to 0 because of how we chose the boundary conditions. Okay. It's not a coincidence how we chose these basis functions and boundary conditions and stuff like that. I'll get to that in a couple of different lectures on, once I sort of give you the overall recipe for how to solve these sorts of problems. Okay, but for now, it's just maybe take a step and be like, hey, this is kind of cool that we were actually able to do this. Okay, we have one more term on this right-hand side. This term looks like this. Integral from 0 to 1 of g times the second derivative of our basis functions. It turns out that the second derivative of our basis function that we can actually take the derivative of, right? We know what our basis function is. Let me write it over on the scratchwork side over here, right? We can take that derivative. Okay, if we take one derivative, then what we'll have is square root of 2 times n pi cosine n pi y, right? The n pi has to come out front. If we were to take another derivative, the derivative of cosine is negative sine. And so what we have here is like that, right? And it turns out that this is just equal to that. Here, I won't write that just gets confusing. Just write it like that, right? Because my basis function looks like this. Well, there's my basis function right here. Okay, so this big integration by parts thing over here, we were able to simplify significantly. The right-hand side now looks like this. The right-hand side now looks like this. Both of these terms on the outside are actually equal to 0. And now this term right here is just equal to this. right? Because this second derivative right here is just equal to negative n pi squared times phi n. And so I basically just plug that in directly over here. Now, do you guys recognize what this is? This is just the dot product of, or inner product of my original function times one of the basis functions. And so this is just equal to that. Okay, so in the couple minutes I have left, I'm actually going to combine all this together. This was our original PDE, right? The left-hand side is equal to this, and the right-hand side is equal to this. So let me just write that all down. The PDE becomes this. Okay. And now you guys can solve that, right? Because this is just an ODE now, right? So the PDE becomes many ODEs. When I say many, I mean infinitely many, right? Because remember, our n can go from 1 to 3 to 4 to 5 all the way up to infinity, right? But that's okay. The solutions to all of them look pretty much the same. You just have to write in terms of n, right? So this becomes many ODEs which we can solve. And that's where we'll end lecture today. Basically, you know, we're basically all the way there. We've taken this PDE up here that we honestly don't know how to solve, right? Or I guess here, which we honestly don't know how to solve because PDEs are difficult. And we were able to convert it into an ODE here, right? We only have a derivative in time now. And I think most of you guys could actually solve this ODE, right? Some of you guys might even be able to stare at it and then tell me exactly what the solutions are going to look like, right? And so there's still a few bookkeeping things that we need to figure out. For instance, like we need to figure out what the boundary conditions for these ODEs are and stuff. We'll get there eventually once we reconvene on Wednesday. But this perhaps gives you a little bit of a roadmap and maybe is trying to convince you why we're doing all this weird integration by parts stuff, why we pick these basis functions and stuff like that. Okay. All right. So I'll end there. Any questions? No. Okay. I'll see you guys on Wednesday.
Dr. Wong, do you mind if I ask my question really quickly, the one that I was like...
Yeah, no problem. I'm going to stop the recording thing real quick.